Hello, and welcome. Perhaps you're lying in bed right now, the room quiet except for distant sounds from the world outside. Or maybe you're simply looking for a moment of calm wonder. Either way, this is a gentle space for us to explore something extraordinary together, something that might change how you think about time itself. In 1999, a team of physicists completed an experiment that shouldn't have been possible. They watched photons, tiny particles of light, behave in ways that seem to violate one of the most basic rules we have, that the past stays fixed, that causes come before effects, that time flows in only one direction. The quantum eraser experiment showed something disturbing, future decisions appearing to reach backward through time, altering events that had already happened. This isn't science fiction. It's not a thought experiment or a theoretical possibility. It happened in a laboratory at the University of Maryland, and it's been verified again and again since then. The results stand unchallenged, published in Physical Review Letters, one of the most respected physics journals in the world. What makes it disturbing isn't just that it challenges our intuitions. Quantum mechanics has been doing that for a century. What's disturbing is that it challenges something deeper, the very foundation of cause and effect, the idea that our past is written and unchangeable, that reality proceeds forward like a story being told one word at a time. Tonight, we're going to explore this experiment together. We'll build toward it gently, understanding the pieces first before we see how they combine into something that breaks our understanding of time. There's no rush. The mystery has waited billions of years to be discovered. It can wait while we take our time understanding it. Let's begin more than 2 centuries ago in 1801, with a physician named Thomas Young who wanted to settle a debate about light. Was it made of particles, tiny bullets flying through space? Or was it a wave rippling like water through some invisible medium? Young designed an elegant experiment. Shine light through 2 narrow slits and see what pattern appears on the wall behind them. If light were particles, you'd expect 2 bright bands on the wall, one behind each slit, like throwing sand through 2 holes in a fence. But that's not what Young saw. Instead, light created alternating bands of brightness and darkness, a distinctive interference pattern. Dark bands appeared in places where light from both slits arrived out of sync, the peaks of one wave meeting the troughs of another, cancelling out. Bright bands formed where waves arrived in sync, reinforcing each other. This could only mean one thing. Light was a wave. Particles don't interfere with themselves. A single grain of sand either goes through one hole or the other. But a wave spreads out, passes through both slits simultaneously, and interferes with itself on the other side. For over a century, this seemed settled, until quantum mechanics arrived and made everything strange again. When scientists repeated Young's experiment with individual photons, sending them one at a time through the slits, the interference pattern still appeared, building up slowly, photon by photon. Each single photon, traveling alone, somehow knew about both slits. It interfered with itself, as if it had passed through both openings simultaneously. Even though it was just one particle, the universe, it seemed, didn't care about our categories. Light was behaving as both particle and wave, depending on what we measured. This schizophrenic nature, sometimes wave, sometimes particle, somehow both, became the foundation of quantum mechanics and the seed of everything strange that would follow. Already, in this simple setup, the disturbing truth about reality was waiting. The double-slit experiment revealed that things don't have definite properties until we measure them. A photon isn't a wave or a particle traveling through space with predetermined characteristics. It exists in a haze of possibility, taking on definite properties only when forced to by measurement. And if measurement can determine whether something is a wave or a particle, what else might it determine? What other aspects of reality might wait in superposition until we look? The double-slit experiment opened a door. We're about to step through it. Now comes the truly strange part. The observation that makes quantum mechanics not just surprising but deeply unsettling. Scientists decided to find out which slit each photon actually went through. They placed tiny detectors at each opening, not to block the light, just to register which path it took. Surely the interference pattern would still appear, right? The photon would still go through both slits, and we'd simply gain information about which path it chose. But the moment the detectors were turned on, the interference pattern vanished completely. Instead of alternating bright and dark bands, two simple bright patches appeared, exactly what you'd expect from particles taking definite paths. The wave behavior disappeared the instant we gained which-way information. Turn the detectors off, the interference pattern returns. Turn them back on, it vanishes again. The very act of checking which slit the photon passes through destroys the wave behavior and forces particle behavior instead. This is the observer effect, though that name is slightly misleading. It's not about consciousness or human awareness. It's about information and interaction. The detectors, by gathering which-way information, fundamentally alter the quantum state. Before measurement, the photon exists in superposition, neither here nor there, neither wave nor particle, but somehow both and neither. The act of measurement collapses this hazy potentiality into a single definite reality. Think about what this means. It suggests that reality at the quantum level is incomplete, fuzzy, indeterminate until something measures it. The photon doesn't secretly know which slit it's going through while we remain ignorant. The universe itself doesn't yet contain that information. Only when we measure, when we force the quantum system to interact with something that registers information, does the photon's path become real in any meaningful sense. This isn't just a limitation of our knowledge, it's a statement about reality itself. Before measurement, the property doesn't exist in a classical sense. It waits in superposition, a ghostly combination of all possibilities. Measurement doesn't reveal a pre-existing truth. It participates in creating that truth. Some find this beautiful. The universe is open, participatory, responsive. Others find it disturbing, reality incomplete without observation, waiting for something to make it real. Perhaps you feel both reactions simultaneously, the wonder and the unease mixing together like waves interfering on a distant screen. Either way, this is where quantum mechanics becomes philosophically radical. Classical physics said the universe exists objectively, doing its thing regardless of whether anyone's watching. Quantum mechanics whispers something different. Perhaps observation completes reality rather than simply revealing it. And if observation can turn waves into particles, if the simple act of gaining information can fundamentally alter what happened, then what else might observation do? How far does this strange power extend? Albert Einstein watched quantum mechanics develop with growing alarm. His theory of relativity had already revolutionized our understanding of space and time, showing that they're relative, flexible, intertwined. But quantum mechanics disturbed him in a way relativity never had. Relativity was strange but deterministic, elegant, complete. Quantum mechanics seemed incomplete, probabilistic, almost mocking the idea of objective reality. God does not play dice with the universe, Einstein famously said. Though what he meant wasn't about religious belief. He meant that reality shouldn't be fundamentally random, shouldn't depend on observation, shouldn't refuse to exist in a definite state until someone measures it. The universe should have an objective existence independent of whether anyone's looking at it. In 1935, working with Boris Podolsky and Nathan Rosen, Einstein published what became known as the EPR paradox, arguing that quantum mechanics must be incomplete. Their logic was elegant. If quantum mechanics were correct and complete, then measuring one particle could instantly affect another particle far away, violating what Einstein called locality, the principle that objects are only influenced by their immediate surroundings. Einstein thought this was absurd. How could measuring a particle here instantly determine the properties of a particle across the galaxy? That would require faster-than-light influence, what he dismissively called spooky action at a distance. Surely, Einstein argued, the particles must carry hidden information determining their properties all along. Quantum mechanics simply couldn't see these hidden variables, making it an incomplete description of reality rather than a true picture. It was a compelling argument. For decades, many physicists assumed Einstein was probably right, that eventually we'd discover the deeper layer of reality that quantum mechanics missed. The wave function, they thought, represented our ignorance, not actual indeterminacy. But Einstein was wrong. Beautifully, elegantly, profoundly wrong. in a way that makes reality even stranger than quantum mechanics initially suggested. In the 1960s, physicist John Stuart Bell showed that if local hidden variables existed, if Einstein's intuition was correct, then certain correlations between entangled particles would have strict limits. You could test whether Einstein or quantum mechanics was right by measuring these correlations and checking if they violated Bell's inequality. Experiments eventually proved what Einstein feared. Quantum mechanics was right. The correlations exceeded Bell's limits. The universe is fundamentally non-local. Measuring one particle can instantly correlate with the properties of another, no matter how far apart they are. Not through hidden variables, not through classical communication, but through genuine quantum entanglement. Einstein's wrongness is perhaps more disturbing than his being right would have been. If he were right, reality would be weird but ultimately comprehensible within classical logic. But he was wrong, which means reality violates our deepest intuitions about separateness, locality, and the independence of distant objects. And if the universe can violate our intuitions about space, if separation is less absolute than it appears, then what about time? If quantum mechanics can connect distant locations instantly, might it also connect different moments? Let's look more closely at what disturbed Einstein so deeply. Quantum entanglement, the phenomenon that links particles across any distance in ways that seem to mock the limits of space itself. Imagine two particles created together in a single quantum event, say, a photon splitting into two lower energy photons through a process called down conversion. These twin photons fly apart, perhaps traveling for miles or even light years, yet they remain connected in a way that defies classical explanation. Each photon, before measurement, exists in superposition, its properties undetermined, hazy, waiting. But here's the strange part. They're not in independent superpositions, they're entangled, their quantum states linked. If you measure one photon and find it polarized vertically, the other photon instantly becomes polarized horizontally, regardless of how far apart they are. Not because one sent a signal to the other, that would require time, but instantly, as if distance meant nothing. This isn't hypothetical, it's been tested exhaustively, and the results are clear. Measure one particle, and you instantly gain information about its entangled partner, even if that partner is across the galaxy. The correlations are stronger than any classical physics could allow, stronger than Einstein's local hidden variables could explain. Bell's theorem made this testable, and experiments confirmed it beyond doubt. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for experiments proving entanglement is real, not just theoretical. The universe truly is non-local at the quantum level. Think about what this means. Two particles, separated by any distance, remain parts of a single quantum system. Space doesn't separate them in the way our everyday experience suggests separation works. They're not really two in the classical sense. They're one system that happens to have parts in different locations. Measuring one doesn't send information to the other. It collapses the shared quantum state both inhabit. From a certain perspective, this is beautiful. The universe is more deeply interconnected than our senses reveal. What appears separate may actually be unified at a fundamental level. Distance is real for macroscopic objects and classical signals, but at the quantum level, entangled particles remain intimately linked regardless of spatial separation. From another perspective, it's deeply disturbing. It means our intuitions about independence and locality are wrong. Objects aren't isolated islands existing independently. The universe contains correlations and connections that transcend space itself. And here's where things get really interesting for our story about time. If quantum mechanics can violate our assumptions about space, if particles can remain connected across any distance, then might quantum mechanics also violate our assumptions about time? If space can be transcended through entanglement, what about the separation between past and future? The question hangs in the air like a photon in superposition, waiting for measurement to make it real. In 1978, physicist John Archibald Wheeler proposed a thought experiment that took quantum strangeness to its logical conclusion. If observation determines whether a photon behaves as wave or particle, what happens if we delay our choice about what to measure until after the photon has already passed through the slits? Wheeler's delayed choice experiment works like this. A photon approaches the double slits. We wait until it's definitely passed through them, committed to whatever path it took. Only then, after the photon has gone through, do we decide whether to measure which slit it used or whether to let it create interference. Classical intuition says the photon's past should already be fixed. It either went through one slit as a particle or through both as a wave. Our later decision to measure shouldn't change what already happened. The past is past, written, unchangeable. But Wheeler's thought experiment suggested something deeply unsettling. Our future choice of measurement might determine the photon's past behavior. If we choose to measure which slit it used, we'll find evidence it went through one slit as a particle. If we choose to allow interference, we'll find evidence it went through both as a wave. The photon's history seems to depend on a decision made after that history already occurred. For years, this remained a thought experiment, fascinating but purely theoretical. The technology didn't exist to actually perform it with the required precision, but Wheeler was confident about what the results would show if we could test it. Quantum mechanics would remain consistent with its strange implications, and the past would prove less fixed than we imagine. In the decades that followed, technology advanced enough to test Wheeler's prediction. Experimenters used beam splitters that could be inserted or removed after a photon had already passed the point where it would have decided its nature. The results confirmed Wheeler's prediction. The choice of measurement made after the photon's journey correlated perfectly with which type of behavior the photon showed. It's as if the photon's past remained undetermined until the future measurement. Not because we were ignorant of what it did, but because the universe itself didn't yet contain that information. The photon existed in superposition of having gone through one slit and both slits, with that superposition collapsing only when the delayed choice finally measured it. Wheeler called this participatory universe, the idea that observation doesn't just reveal reality but participates in creating it, even retroactively. The cosmos in this view is not a movie being played for us to watch passively. It's more like an improvisational performance where our measurements help write the script, even the parts that seem like they should already be written. This was disturbing enough, but Wheeler's delayed choice experiment was just a conceptual warm-up, preparing our minds for something even stranger, because the quantum eraser experiment would take this same logic and push it further, making the retrocausal implications undeniable and measurable in ways that shake the foundations of causality itself. Take a moment to notice where we are in this journey. We've assembled all the pieces now, like gathering ingredients before attempting a recipe that will yield something unprecedented, something that challenges our most basic assumptions about how reality works. We have wave-particle duality, the strange fact that quantum objects don't have definite classical properties until measured, existing instead in superposition of multiple possibilities simultaneously. We have the observer effect, the disturbing discovery that measurement doesn't reveal pre-existing properties, but rather participates in determining them, collapsing superposition into classical definiteness. We have entanglement, the proved reality that quantum correlations transcend space, linking particles across any distance in ways that violate our intuitions about locality and separation. We have delayed choice, Wheeler's demonstration that measurement can seemingly determine properties retroactively, with future choices correlating with past behaviors as if time's arrow could bend backward. Each of these is strange enough on its own, but like musical notes that sound consonant individually yet create unsettling harmonies when played together, these quantum phenomena combine into something that goes beyond mere strangeness. They combine into the quantum eraser experiment, a setup that makes retrocausality not just theoretically possible, but experimentally demonstrable. The quantum eraser takes entanglement's transcendence of space and delayed choices' suggestions about time, then merges them in a way that forces us to confront something disturbing. The future might genuinely reach back to influence the past, not metaphorically, not as a limitation of our knowledge, but as an actual feature of how quantum reality operates. Perhaps you can feel it building, This sense that we're approaching something significant, like standing at the edge of a forest at dusk, about to step into darkness deeper than expected. There's wonder here, certainly. The universe is about to reveal how much stranger it is than we imagined. But there's also unease, because what we're about to explore challenges the very concept of causality, the idea that causes precede effects, that time flows in only one direction, that the past stays fixed while only the future remains open. In 1999, a team led by Yoon-ho Kim performed an experiment at the University of Maryland that brought all these elements together. What they found has disturbed and fascinated physicists ever since. The quantum eraser experiment stands as one of the clearest demonstrations that quantum mechanics isn't just weird, it's weird in ways that specifically challenge our understanding of time itself. The stage is set, the pieces are assembled. Now we're ready to see how they combine into something that breaks our understanding of past and future. Let's look at what they actually did. The quantum eraser experiment, as performed by Yoon-ho Kim and colleagues, sounds deceptively simple. Take a laser, split photons into entangled pairs, send them on different paths, detect them separately, and analyze the correlations. But the genius lies in the geometry, in precisely how these elements arrange to make the impossible visible. At the heart of the setup sits a nonlinear crystal, specifically beta-barium borate, that performs down conversion. When a high-energy photon from a laser passes through this crystal, it occasionally splits into two lower-energy photons. These twin photons are entangled, their quantum states linked regardless of how far apart they travel. For our purposes, we'll call one the signal photon and the other the idler photon. Though they're perfectly symmetrical in the physics, the signal photon heads toward a double-slit setup, or more precisely, two closely positioned down conversion locations that function like slits. After passing through, the signal photon travels a short distance to a detector that simply registers its arrival position. This is where the interference pattern might or might not appear, depending on what happens next. The idler photon takes a longer path, winding through a series of mirrors and beam splitters before finally reaching one of 4 detectors. This longer path is crucial. It means the idler photon arrives at its detector nanoseconds after the signal photon has already been detected and recorded. This timing difference is what makes the experiment's retrocausal implications so disturbing. Here's where the setup gets elegant. The idler photon encounters a beam splitter that can either preserve which-way information or scramble it. If the beam splitter preserves information, we can tell which of the two slits the original photon pair came from by seeing which detector the idler hits. If the beam splitter scrambles the information, that which-way knowledge becomes permanently erased, not hidden, but genuinely unknowable, destroyed at the quantum level. The setup physically embodies the question: what happens when we erase which-way information after the signal photon has already been detected? Does the signal photon's behavior somehow know about the future erasure? Does its interference pattern depend on what happens to its entangled twin nanoseconds later? The apparatus itself seems designed to break causality. Signal photons hitting the detector first, creating their pattern. Idler photons arriving later, with future events determining whether information gets erased. The geometry arranges things so that effect precedes cause, at least in our conventional understanding of those terms. Kim's team built this apparatus with exquisite precision, every path length calibrated to the nanometer, every detector timed with incredible accuracy, the entire system designed to catch reality in the act of violating our assumptions about time's arrow. And when they ran the experiment, the apparatus delivered exactly that: clear, reproducible evidence that future events correlate with past outcomes in ways that challenge our most basic notions of causality. Let's run the experiment first in its classical mode, where everything behaves as our intuitions expect and the disturbing implications remain hidden. In this configuration, we preserve which-way information. The idler photon's path tells us definitively which of the two down conversion locations produced each entangled pair. We can track, for every signal photon that hits the detector, exactly which slit it originated from. The information exists in the universe, encoded in the idler photon's trajectory. When we look at the signal photon's detection pattern in this mode, we see exactly what classical physics predicts. Two bright patches, one corresponding to each origin point. No interference pattern appears. No alternating bright and dark fringes, just two simple bright regions where signal photons arrive, bunched around the positions aligned with their origin locations. This makes perfect sense classically. If each photon has a definite path, a specific origin point, then it behaves as a particle taking that single path. Particles don't interfere with themselves. They travel from point A to point B, and we can in principle track their journey completely. The which way information exists, and the photons behave accordingly, like little bullets following ballistic trajectories. Everything here is normal, classical, undisturbing. The signal photons arrive at the detector. The idler photons arrive nanoseconds later at their own detectors. We correlate which signal photons matched with which idler photons by matching their arrival times. When we sort the signal photons based on their idler partners' destinations, we find two distinct populations, each showing a simple bright patch with no interference. It's almost boring in its ordinariness. Particles acting like particles, taking definite paths, creating patterns that Newton himself would have understood perfectly well. The quantum nature hides beneath behavior that looks classical for all practical purposes, but this classical behavior is just the control condition, the baseline against which we'll measure something far stranger. This is physics behaving itself, following rules that match our intuitions about how reality should work. Causes precede effects. The past determines the future. Information flows forward through time. We need to understand this normal mode to appreciate what happens when we change one simple thing, when we introduce the quantum eraser and destroy the which way information. Because when that information gets erased, when the universe loses the ability to tell which path the photons took, everything changes. The signal photons' behavior changes, their detection pattern transforms. And the disturbing part, the part that breaks our understanding of causality, is that the signal photons hit their detector before the erasure happens. Their behavior seems to anticipate an event that hasn't occurred yet, an event that lies in their future. But we're getting ahead of ourselves. First, let's understand exactly what the quantum eraser does, and how information gets destroyed at the fundamental level. Now we change the configuration. We introduce the quantum eraser, a second beam splitter in the idler photon's path that does something remarkable. It makes the which way information fundamentally unknowable. This beam splitter sits at a crucial junction where the two possible idler paths converge. When the idler photon reaches this point, the beam splitter gives it an equal probability of being transmitted or reflected. But here's the key: both paths lead to detectors, and the beam splitter is positioned so that an idler photon could have reached it from either original source. What does this mean? It means that when an idler photon passes through this erasing beam splitter and hits one of the two detectors beyond it, we genuinely cannot tell which path it took to get there. Both original sources could have led to this detector via different routes through the beam splitter. The which way information doesn't just become difficult to access, it becomes genuinely fundamentally unknowable. This isn't about our ignorance. This is about the universe itself no longer containing that information. The quantum state has been scrambled in a way that destroys the correlation between the idler's final destination and the entangled pair's origin. Even if we knew every single quantum detail about the idler photon when it hits the eraser detector, we couldn't work backward to determine which path it took. The information has been erased at the quantum level, not hidden, not encrypted, but genuinely eliminated from reality. Now here's where things get disturbing. The signal photon hit its detector nanoseconds before the idler photon reached this erasing beam splitter. The signal photon was detected, recorded, its position noted. At that moment, the which way information still existed in the universe, encoded in the idler photon that was still traveling toward the beam splitter. Only after the signal detection, after that moment has passed and been recorded, does the idler photon encounter the erasing beam splitter and have its information scrambled and destroyed. Past meets future at this junction. The signal photon's behavior, its position, whether it participates in interference, gets recorded in the past. The which-way information gets erased in the future, and somehow, impossibly, these two events correlate in a way that suggests the future erasure affects the past behavior. When researchers sort the signal photons based on which eraser detector their idler partners eventually hit, they find something impossible. Interference patterns appear, not in the total signal, but in these sorted subsets. The signal photons that get paired with idlers taking certain eraser paths show wave-like interference. Those paired with idlers taking other eraser paths show different patterns, but the signal photons hit their detector first. They were detected before their idler partners encountered the eraser. How can their behavior depend on an event that hasn't happened yet? This is the quantum eraser effect. This is where causality seems to break down. This is what's disturbing. Let's focus on the timing, because this is where the disturbing nature of the quantum eraser becomes undeniable and impossible to explain away with classical intuitions. The signal photon travels a short path, let's say about 40 centimeters from the down conversion crystal to its detector. Light travels at roughly 30 centimeters per nanosecond, so this journey takes just over 1 nanosecond. The photon arrives, interacts with the detector, and its position gets recorded. This happens at time t. The idler photon, meanwhile, travels a much longer path, several meters, winding through mirrors and beam splitters. It doesn't reach its destination until time t plus several nanoseconds. The exact delay varies by setup, but the key point is absolute and undeniable. The signal arrives first, the idler arrives later. At time t, when the signal photon hits its detector, the which-way information still exists in the universe. It's encoded in the idler photon, which is still in flight, still carrying information about which source location the entangled pair originated from. At this moment, if we froze time and examined the quantum state of the universe, we could in principle determine which path the signal photon took. Only after time t, only after the signal has been detected and recorded, does the idler photon reach the quantum eraser beam splitter. Only then does the which-way information get scrambled and destroyed. Only in the future, relative to the signal detection, does the erasure happen. And yet, and this is the disturbing core of the experiment, when we later analyze the signal photons by sorting them according to their idler partners' final detectors, we find patterns that depend on whether the which-way information got erased or not. Signal photons whose idler partners went to certain eraser detectors show interference patterns, the characteristic wave behavior that only appears when which-way information doesn't exist. Signal photons whose idler partners went to other detectors show particle-like patterns, no interference, just simple bright patches. The signal photon's behavior, recorded at time t, correlates perfectly with the erasure event that happens at time t plus several nanoseconds. The past correlates with the future. Effect seems to precede cause. Think about what this means gently, letting the strangeness settle like snow. A photon hits a detector, creating a particular pattern, at a moment when information about its path still exists in the universe. Nanoseconds later, that information gets erased, and somehow, the photon's earlier behavior knew about this future erasure, behaving like a wave if information would be erased, like a particle if information would be preserved. Causality says the past determines the future, but here, the future seems to reach back and determine the past. The signal photon's wave or particle nature appears to depend on a choice made after it was already detected. This is what breaks our understanding. This is why the quantum eraser is disturbing. Not just counterintuitive, genuinely challenging to the concept of time's arrow. The full beauty and disturbing nature of the quantum eraser becomes clearest when we look at all four detectors in the idler path. 2 that preserve which-way information, and 2 that erase it. Let's label them D1, D2, D3, and D4. D1 and D2 are positioned so that an idler reaching them must have come from a definite source. One path leads to D1, the other to D2. When an idler hits these detectors, which-way information is preserved, we can tell which origin the entangled pair came from. D3 and D4 sit beyond the erasing beam splitter, positioned so that idlers from either source could reach them through different routes. When an idler hits these detectors, which way information is erased, we cannot tell which origin the entangled pair came from, not even in principle. Now we collect signal photons over many experimental runs, thousands or millions of them. At first, looking at all the signal photons together without sorting, we see no interference pattern, just a broad distribution of hits across the detector. Nothing special, nothing disturbing. But then we sort them. We take only those signal photons whose idler partners eventually hit D1. When we plot these, we see a simple bright patch, particle behavior, no interference. Makes sense. D1 preserved which way information. We take signal photons whose idlers hit D2. Another simple bright patch, slightly offset from the first. Again, particle behavior. Still makes sense. Now comes the disturbing part. We take signal photons whose idlers hit D3. We plot their positions, and there, clear and undeniable, is an interference pattern, alternating bright and dark fringes, the signature of wave behavior. These signal photons behaved as if they went through both slits, even though each individual photon seems like it should have gone through one or the other. We take signal photons whose idlers hit D4. Another interference pattern appears, shifted in phase from the D3 pattern. More wave behavior, more interference. Stop and appreciate what just happened. The signal photons were all detected at the same time, all hitting their detector nanoseconds before any idler reached its final destination. Yet when we sort them by future events, by which detector their idler partners eventually reached, we find that some behaved as waves and others as particles. The sorting reveals 4 distinct patterns, each predicted perfectly by quantum mechanics. D1 and D2 show particle behavior. D3 and D4 show wave behavior. The signal photon's nature, wave or particle, correlates perfectly with whether the which way information eventually got erased, even though the signal was detected first. Each signal photon somehow knew which detector its entangled partner would eventually reach. It knew whether information would be preserved or erased. It behaved accordingly, as particle when information would survive, as wave when information would be destroyed. Despite this determination happening in its future, this is retrocausality made visible. This is the future influencing the past, demonstrated with such clarity that it cannot be dismissed as experimental error or theoretical speculation. Before we spiral into paradoxes and disturbing implications, let's address the obvious question. If the future can influence the past, why can't we send messages backward through time? Why can't we use this to create grandfather paradoxes, lottery-winning schemes, or warnings about disasters before they happen? The answer lies in a subtle but crucial detail. You need information from the future to see the retrocausal effect. Remember, when we first look at all the signal photons together, before sorting them by their idler partners' destinations, we see no interference pattern, just a broad, featureless distribution. There's no message there, no signal, nothing that indicates anything special happened. Only when we sort the signal photons using information from the future, specifically which detector each idler photon eventually hit, do the interference patterns emerge. We need to know where the idlers went, which means we need to wait for them to arrive. We need the future to complete before we can see how it correlated with the past. This preserves causality in a weird way. Yes, the signal photon's behavior depends on the future erasure, but no one can know this until after the erasure happens. The retrocausal correlation exists, but it's only visible retrospectively after both events have occurred. You can't use this to send messages backward because any message would require choosing to erase or not erase information, then having someone in the past see the result before the future choice is made. But they can't see the result without sorting the data, and they can't sort the data without knowing which detector each idler hit, and they can't know that until after the idlers arrive. The universe maintains logical consistency through this clever restriction. It permits retrocausal correlations, future events influencing past outcomes, but prevents retrocausal communication, information flowing backward to create paradoxes. Think of it like this. The past and future are correlated, but the correlation only becomes visible when you have information from both ends. Until then, each moment looks random, uncertain, consistent with multiple possibilities. Only retrospectively, looking back with complete information, do you see how future events aligned perfectly with past behaviors. This is still deeply disturbing, just in a different way. It means the universe contains a causal correlations, connections between events that can't be explained by normal cause and effect. The past and future are linked in ways that transcend time's arrow, but these links are subtle, hidden, revealing themselves only when we know both ends of the correlation. Nature preserves logical consistency while permitting something that seems impossible. Genuine influence flowing backward through time, visible only when we look backward from the future we're trying to influence. The quantum eraser shows us a universe stranger than paradox, more subtle than our classical intuitions, disturbing in ways that challenge our deepest assumptions while somehow remaining internally consistent. Let's take the retrocausal interpretation seriously for a moment, letting ourselves feel the full weight of what it implies. If we accept the quantum eraser results at face value, what are we actually claiming about reality? We're saying that future events, specifically whether which way information gets erased or preserved, reach backward through time to determine past events, specifically whether signal photons behave as waves or particles, not metaphorically, not as a limitation of knowledge, but genuinely physically, with future measurements completing the past's quantum state. John Wheeler, who proposed many of these ideas, called this the participatory universe. In his view, the cosmos isn't a stage where observers watch a predetermined performance. It's more like an improvisational collaboration where observation actively participates in creating reality, even retroactively. The act of measurement doesn't reveal pre-existing properties. It completes them, makes them real, brings them into definite existence. In this interpretation, the signal photon doesn't secretly know whether it should behave as wave or particle when it hits the detector. At that moment, it genuinely exists in superposition of both behaviors. Only when the future measurement happens, when the idler hits an eraser detector or a which-way detector, does the superposition collapse retroactively, determining which behavior the signal photon manifested. The past, in this view, remains somewhat open, unfixed, indeterminate until future measurements complete it. Not because we're ignorant of what happened, but because the universe itself doesn't yet contain that information. Reality waits in quantum potentiality until observation transforms it into classical actuality. This creates a strange loop of causation. The future measurement depends on the past setup, where beam splitters were placed, which paths existed, but the past behavior depends on the future measurement, which detector the idler eventually hit. Cause and effect form a circle, each influencing the other across time. Some find this philosophically beautiful. It suggests the universe is fundamentally relational, with events gaining meaning through their connections to other events across time. Nothing exists in isolation. Everything participates in a vast web of correlations spanning past and future. Others find it disturbing, and understandably so. It challenges our basic sense that the past is fixed and only the future remains open. It suggests that decisions we make now might reach backward to influence events already recorded. It makes causality less absolute, more contextual, dependent on which measurements we choose to make. Wheeler embraced this strangeness. He proposed cosmic delayed choice experiments, where observations we make today might reach back billions of years to influence events near the Big Bang. Perhaps the early universe existed in superposition until conscious observers evolved to measure it. Perhaps we're literally creating the cosmos's past through our present observations. It's dizzying, this vertigo of collapsed temporal certainties, the future reaching back, the past waiting to be determined. Reality is collaboration between moments that we thought were separate. Not everyone accepts retrocausality. Many physicists find it too disturbing, too challenging to fundamental notions of causation. They seek alternative interpretations that preserve a more conventional relationship between past and future. The most prominent refuge the many worlds interpretation proposed by Hugh Everett III. In Everett's vision, quantum superposition never collapses. Instead, every quantum possibility becomes real in its own branch of reality. When a measurement occurs, the universe splits into multiple versions, each experiencing a different outcome. All possibilities actualize, just in different parallel universes. Applied to the quantum eraser, this interpretation works like this. When the signal photon approaches the detector, the universe branches into versions where it takes every possible position. This branching creates a pattern, a distribution of outcomes across the multiverse that includes both wave-like and particle-like possibilities simultaneously. When the idler photon reaches its destination, the universe branches again based on which detector it hits. But here's the key. These branchings are correlated by the initial entanglement. The branches where the idler goes to an eraser detector are the same branches where the signal showed wave behavior. The branches where the idler goes to a which-way detector are the branches where the signal showed particle behavior. From inside any single branch, it looks like the signal photon's behavior depended on the future erasure. But in the many worlds interpretation, there's no actual backward causation. Both events were determined by the initial quantum state. We just experienced them sequentially and noticed their correlation afterward. The signal didn't know the future. Rather, we find ourselves in a branch where both events correlate in a particular way. This preserves forward causation at the cost of ontological extravagance. Instead of one universe with retrocausality, we get infinite universes with normal causality in each one. The disturbing backward influence gets replaced by mind-boggling proliferation of parallel realities. Many find this less disturbing than retrocausality. Causality is preserved, nothing reaches backward. The apparent correlations emerge from branching structure rather than temporal influence. Past events don't depend on future measurements. We simply experience one branch where they correlate in a particular way, but the cost is steep. Every quantum event splits reality into multiples. Every measurement creates branches. The quantum eraser experiment alone spawns countless parallel universes, each experiencing different correlations between signal and idler detections. The universe becomes infinitely larger, more complex, more profligate with reality. And there's a deeper question. Do we really avoid the disturbing implications? The correlation between signal and idler still exists, still needs explanation. Whether we call it backward causation or branching correlation, something non-classical links past and future in ways our intuitions struggle to grasp. Perhaps many worlds is less disturbing emotionally, no spooky backward influence, but it's arguably more disturbing ontologically. Instead of questioning time's arrow, we're questioning the uniqueness of reality itself. Instead of one past reaching toward multiple possible futures, we get multiple parallel pasts and futures, all existing simultaneously. Different disturbing, perhaps, but still disturbing. Another escape route. Perhaps quantum mechanics isn't the complete picture. Perhaps beneath the apparent randomness and retrocausality lies a deeper deterministic layer we haven't discovered yet. Hidden variables that determine outcomes before measurement, preserving classical causality. The most developed hidden variable theory is de Broglie-Bohm mechanics, also called pilot wave theory. In this interpretation, particles always have definite positions and velocities, guided by a quantum wave that tells them where to go. Nothing is truly random or indeterminate. Everything is deterministic, just guided by a wave we can't fully see. Applied to the quantum eraser, Bohmian mechanics works like this. Both signal and idler photons have definite trajectories from the start, determined by the initial quantum state. The signal photon takes a specific path and hits a specific location on its detector. The idler photon follows its own specific path toward its eventual detector. These trajectories are correlated from the beginning through the entanglement of their guiding waves. When we observe wave behavior, it's because the guiding wave creates trajectories that bunch up and spread out in patterns matching interference. When we observe particle behavior, it's because the trajectories follow simpler paths. Which type of trajectory each photon follows is determined at the moment of down conversion, not by future measurements. The apparent retrocausality disappears. The correlation between signal behavior and idler destination isn't the future influencing the past. It's both being determined by the same initial quantum state. We see them as temporally separated, but they're both manifestations of a single deterministic unfolding. This preserves determinism and forward causation. Nothing reaches backward through time. The past is completely fixed, determined by initial conditions and dynamical laws. The quantum eraser correlations emerge from these hidden deterministic trajectories, not from future influence. But this comfort comes at a cost. The guiding wave must be non-local. It must instantaneously connect distant parts of the universe to maintain correlations between entangled particles. The signal photon's trajectory depends on the idler photon's guiding wave, even when they're far apart. Space gets violated to preserve time, so Bohmian mechanics trades one disturbing feature for another. Instead of retrocausality, we get instantaneous action at a distance. Instead of future influencing past, we get distant locations influencing each other faster than light. We've solved the time problem by accepting a space problem, and many physicists find the non-local guiding wave just as strange as quantum superposition, perhaps stranger because it's hidden, unobservable except through its effects. We've replaced visible strangeness with invisible strangeness, traded quantum fuzziness for classical definiteness at the cost of introducing an unobservable field connecting everything. Still, for those who find retrocausality particularly disturbing, Bohmian mechanics offers refuge. It shows that the quantum eraser doesn't necessarily prove the future influences the past. It might just reveal deeper deterministic structures we haven't fully mapped yet. Structures that look retrocausal only because we're seeing partial information. Different interpretation, different disturbing implications, same experimental results. The quantum eraser data remains regardless of how we explain it. John Wheeler, who contributed so much to our understanding of quantum mechanics and relativity, proposed a radical idea late in his career. It from bit. Reality, he suggested, isn't fundamentally material. It's fundamentally informational. Physical properties emerge from relationships and knowledge, not from objective properties existing independently. In this view, the quantum eraser experiment reveals something profound about information's role in determining reality. It's not that particles have definite properties that measurements reveal. It's that information accessibility determines which properties become real. When which way information exists, when the universe contains data about the photon's path, particle behavior manifests. When which way information is erased, when the universe loses that data, wave behavior manifests. The physical properties depend not on hidden objective facts, but on what information exists in the universe at any given moment. This interpretation takes quantum mechanics' observational dependence seriously, but shifts the emphasis. It's not about consciousness or human awareness. It's about information itself as a fundamental aspect of reality. Physical properties aren't pre-existing features waiting to be discovered. They're emergent consequences of informational relationships. The quantum eraser's retrocausal appearance emerges naturally from this view. When we erase information in the future, we're changing what the universe knows about the photon's path. That change in knowledge determines which properties are real, which behaviors manifest. The past state depends on future information because physical states are informational states. Think of it this way: the signal photon exists in a superposition of wave and particle behavior. Which one becomes real depends on whether which way information exists. That information exists in the idler photon initially. When the idler encounters the erasing beam splitter, the information gets destroyed. At that moment, the universe's informational state changes, and the signal photon's behavior gets determined retroactively based on what information exists. This is still disturbing, but disturbing in a different way. Instead of questioning time's arrow, we're questioning the nature of physical reality itself. Instead of matter as primary with information secondary, we get information as primary with matter as emergent. Instead of objective properties existing independently, we get properties arising from relationships and knowledge. Wheeler pushed this idea to cosmic scales. Perhaps the entire universe is fundamentally a network of information, with physical properties emerging from how that information organizes and relates to itself. Perhaps what we call matter and energy are surface features of deeper informational structures. The quantum eraser, in this view, isn't proving that time can run backward. It's revealing that reality is more informational than material, more relational than objective, more participatory than observer-independent. The disturbing part isn't retrocausality per se, it's the dissolution of objective physical properties into informational relationships. Some find this beautiful. Reality is fundamentally participatory, with observation and knowledge playing constitutive roles in determining what exists. Others find it troubling. What happened to objective reality? To the universe existing independently whether anyone's watching or not? Wheeler embraced the strangeness with characteristic boldness. Information isn't secondary to physics, it is physics at the deepest level. Perhaps the deepest lesson of the quantum eraser is humility. Our intuitions about time, causality and reality are built from macroscopic experience. Objects we can touch, events we can watch, causes and effects we can trace. At the quantum level, these intuitions simply fail, not because they're wrong about everyday reality, but because they're incomplete guides to fundamental reality. Consider time's arrow. We experience time flowing from past to future, driven by entropy's increase. Hot coffee cools, eggs scramble but don't unscramble, memory points backward, anticipation forward. This arrow feels absolute, fundamental, built into the fabric of reality. But at the microscopic level, physical laws are time-symmetric. If you film particles interacting and run the footage backward, you can't tell which direction is forward in time. The laws work equally well both ways. Time's arrow emerges from statistical patterns in complex systems, not from fundamental physical laws. The quantum eraser reminds us of this. At the quantum level, correlations can connect past and future without respecting our macroscopic sense of causation. The statistical arrow of time, entropy increasing, macroscopic processes running one direction, remains intact, but the fundamental laws permit correlations and influences our intuitions reject. Our macroscopic experience misleads us. We think the past is fixed because we remember it and can't change it. We think causes must precede effects because that's what we observe in complex systems. We think observation reveals rather than participates because our measurements barely disturb macroscopic objects. But these intuitions are local adaptations, useful heuristics for navigating a complex classical world. They're not deep truths about fundamental reality. At the quantum level, the past isn't fixed until observed. Effects can correlate with future causes. Observation fundamentally participates in determining outcomes. This is the disturbing lesson. Trust physics over intuition when they conflict. Not because intuition is worthless, it serves us well in everyday life, but because reality at fundamental scales operates differently than our evolved intuitions expect. Some resist this lesson, insisting quantum mechanics must eventually be explained in classical terms, but decades of experiments, including the quantum eraser, suggest otherwise. Reality at the quantum level is genuinely fundamentally different from macroscopic reality, not just smaller or faster, but ontologically distinct. The quantum eraser specifically challenges temporal intuitions. It shows that correlations between events don't require the earlier event to cause the later one in any classical sense. Past and future can be linked in ways that transcend our notion of time's arrow, without creating logical paradoxes or allowing science fiction causality violations. This requires expanding our conceptual framework. Instead of thinking about causation as strictly forward-flowing, we need frameworks that accommodate acausal correlations, retrodictive influences, participatory completion of the past. Instead of time as an absolute river flowing one direction, we need time as more subtle, more relativistic, more quantum. The disturbing part isn't that we need to abandon reason or logic, it's that we need to abandon intuitions that seemed as certain as reason itself. If the quantum eraser challenges our understanding of causality this deeply, perhaps we need to rethink time itself. What is time really, beneath our experience of past flowing into present, flowing into future? Einstein's relativity already questioned absolute time. In his framework, different observers moving at different velocities experience time differently. What's simultaneous for one observer isn't simultaneous for another. Time and space interweave into space-time, a four-dimensional fabric where now is relative, not absolute. This gave us the block universe, the idea that all moments exist equally, spread out across space-time like pages in a book. Past, present, and future are all equally real, just located at different positions in the temporal dimension. We experience time as flowing because our consciousness moves through this block, but the block itself is static, eternal, containing all moments simultaneously. The quantum eraser adds new strangeness to this picture. If future measurements can determine past states, then even the block universe isn't quite static. Or perhaps it's better to say that quantum mechanics reveals correlations in the block that transcend our notion of earlier and later. Events in our future and our past are linked in ways that don't respect temporal ordering. Some physicists suggest time might be emergent rather than fundamental, something that appears in complex systems but doesn't exist at the deepest level of reality. In this view, fundamental physics is timeless, just quantum states and their relationships. Time emerges when we look at these timeless structures from inside, from the perspective of a system entangled with its environment, accumulating records we call memories. If time is emergent, then maybe retrocausality isn't violating a fundamental law. It's revealing the timeless correlations beneath our temporal experience. The quantum eraser shows us glimpses of reality's timeless layer, where past and future are just different aspects of a single quantum state. This is profoundly disorienting. We think of ourselves as moving through time, from past through present toward future, but perhaps that motion is illusory, a perspective effect from living inside a timeless quantum structure. Perhaps the past, present, future sequence is like the sequence of pages in a book, useful for reading, but all existing simultaneously in a higher dimensional reality. Wheeler took this even further with his participatory anthropic principle. Perhaps the early universe existed in quantum superposition until conscious observers evolved to measure it. Perhaps our observations now, billions of years after the Big Bang, reach backward to complete the universe's initial quantum state, determining which particular universe we inhabit. It sounds absurd, but if quantum mechanics permits retrocausal correlations on nanosecond scales in laboratories, why not on cosmic scales across billions of years? Perhaps the universe's past is genuinely undetermined until future measurements complete it. Perhaps we're participants in creating cosmic history, not just observers of it. The quantum eraser doesn't prove these radical ideas, but it suggests that time's nature is far stranger than our experience reveals, that the boundaries between past and future may be less absolute than they seem, that reality's temporal structure might be fundamentally different from what our intuitions suggest. When quantum mechanics reveals that observation matters, that measurement determines outcomes, that reality seems incomplete until someone looks, it's natural to wonder, what about consciousness? Does awareness play a special role in collapsing quantum states and completing reality? Some interpretations of quantum mechanics embrace this idea. Von Neumann proposed that quantum superposition collapses only when it reaches consciousness, that physical measurements alone aren't enough, you need a conscious observer to complete the chain and determine outcomes. Eugene Wigner extended this, arguing that consciousness stands outside the quantum mechanical description, serving as the final arbiter of what becomes real. In this view, the quantum eraser would work only because conscious observers eventually analyzed the data. The signal photons remain in superposition until someone consciously observes which detector their idler partners hit. Consciousness reaching backward through the data completes the measurement retroactively. It's tempting. It seems to elevate mind to a fundamental role in physics. It appears to solve the measurement problem by making consciousness the boundary between quantum and classical. And for some, it carries philosophical or spiritual satisfaction. The universe needs observers, needs consciousness to become real. But most physicists reject consciousness-based interpretations, and the quantum eraser shows why. The experiment works whether or not anyone consciously examines the results. The correlations exist in the data regardless of human awareness. You could run the experiment, store the results on a hard drive, and delete them before anyone looks. the quantum correlations would still have existed, the retrocausal patterns would still have been there, even if no consciousness ever accessed them. What matters for quantum mechanics is interaction and decoherence, not consciousness. When the idler photon hits a detector, that's a measurement, a physical interaction that couples the quantum system to a macroscopic device, creating irreversible records in the environment. Consciousness isn't needed for this. Physical interaction suffices. The quantum eraser specifically uses physical erasure, not conscious forgetting. The beam splitter scrambles which way information quantum mechanically, making it physically impossible to determine the path, not just difficult for human minds to figure out, but genuinely unknowable even in principle. The erasure is physical, objective, consciousness independent, yet the measurement problem remains disturbing even without consciousness. What exactly counts as measurement? When does superposition collapse into definite classical states? Decoherence provides practical answers. Superposition gets destroyed incredibly fast when quantum systems interact with complex environments. But it doesn't fully solve the conceptual problem of why measurement seems special. Perhaps consciousness seems relevant because conscious beings create contexts where quantum strangeness becomes visible. We design experiments, arrange apparatus, analyze results. We create the conditions where quantum mechanics reveals its strange features, not because consciousness collapses superposition, but because conscious experimenters ask questions in ways that make quantum correlations visible. The quantum eraser doesn't need consciousness to work, but it needs conscious understanding to appreciate. The disturbing implications exist whether or not anyone notices them, but their significance, what they mean for our understanding of reality, requires minds capable of grasping the strangeness. What measurements mean remains unclear even after a century of quantum mechanics, but consciousness-based explanations create more problems than they solve. Wheeler's delayed choice experiments suggest something radical. Perhaps the past isn't fully determined until we measure it. What if we apply this idea at cosmic scales to the universe's history itself? Consider a distant quasar, light from which has been traveling toward Earth for billions of years. That light, when it reaches us, can take different paths, bent around a massive galaxy serving as gravitational lens, creating multiple images of the same quasar. By choosing how we measure the light now, we can determine whether it behaved as wave or particle during its billion-year journey. If we measure which path the light took around the gravitational lens, placing detectors that distinguish the paths, we find it behaved as a particle, taking one definite route. If instead we let the paths interfere, using mirrors to combine them without determining which path was taken, we find wave behavior, interference patterns suggesting the light took both paths simultaneously. Wheeler proposed this cosmic delayed choice experiment decades ago. And here's the disturbing implication. Our choice of measurement now in 2025 determines how the light behaved billions of years ago when the quasar emitted it and when it passed the gravitational lens. The photon's ancient history depends on our present-day experimental choice. Did the early universe have definite properties, definite positions for galaxies, definite states for quantum fields, before we evolved to measure them? Or did cosmic history exist in quantum superposition until conscious observers emerged to collapse it? This is participatory cosmology, the idea that observation doesn't just reveal the universe's past, but participates in completing it. Perhaps the Big Bang itself existed in quantum superposition until beings capable of measuring it eventually appeared. Perhaps we're literally selecting which cosmic history became real through our present observations. It sounds like solipsism, like the universe couldn't exist before observers, but it's subtler than that. The quantum state existed, space-time, matter, energy, all present, but perhaps specific classical properties, definite positions, definite outcomes, remained undetermined until measurements collapsed the superposition. The universe was real, just not classically definite in all details. Think about what this means for cosmic evolution. Perhaps the laws of physics themselves existed in some superposition of possibilities, until observers appeared to measure outcomes that depended on those laws. Perhaps the fundamental constants, the speed of light, the strength of gravity, became definite through anthropic selection when conscious beings emerged. This connects to the anthropic principle, the observation that the universe's properties seem remarkably fine-tuned for life. Perhaps this isn't coincidence. Perhaps we observe these particular properties because our observation selected them from a quantum superposition of possible cosmic histories. The properties are fine-tuned for us because our existence required and therefore selected that fine-tuning. It's dizzying. Instead of the universe existing objectively for billions of years before we appeared, we might be retroactively completing cosmic history through our present observations. Instead of being late arrivals in a predetermined cosmos, we might be participants in creating the past we observe. The quantum eraser doesn't prove this cosmic retrocausality, but it demonstrates that retrocausal correlations exist, that future measurements can determine past states, that quantum mechanics permits influence flowing backward through time. If it works for nanoseconds in laboratories, why not for billions of years in the cosmos? The quantum eraser isn't alone in suggesting retrocausality. Other experiments and theoretical frameworks point towards similar conclusions, building a broader pattern that challenges our understanding of time's arrow. Yakir Aharonov and colleagues developed the two-state vector formalism, which treats quantum systems with boundary conditions from both past and future. In normal quantum mechanics, we specify initial conditions and calculate forward to predict future probabilities. In two-state vector formalism, we specify both initial conditions past and final conditions future, then calculate what happens in between. This formalism reveals weak measurements, subtle observations that barely disturb quantum systems. With weak measurements, you can seemingly detect properties that don't exist in standard quantum mechanics, and some of these measurements suggest backward influence, future boundary conditions affecting past weak measurement outcomes. The Aharonov-Bergman-Lebowitz formula describes this mathematically, showing how quantum probabilities depend on both past preparation and future measurement. It's explicitly time-symmetric. Past and future play symmetric roles in determining present probabilities. The quantum state is fully specified only when you know both where the system came from and where it's going. Retrocausality appears in other quantum experiments too. The quantum eraser is perhaps the clearest demonstration, but variations exist showing similar effects. Some use atoms instead of photons, others use different detection schemes. All reveal the same disturbing pattern: future events correlating with past outcomes in ways that challenge normal causality. Even quantum field theory, our most fundamental description of particles and forces, contains elements that look retrocausal when interpreted carefully. The Feynman-Stueckelberg interpretation treats antiparticles as particles moving backward through time. Feynman diagrams, our visual tool for calculating quantum interactions, implicitly contain this temporal symmetry. Some physicists argue we should take retrocausality seriously as a fundamental feature of quantum mechanics, not an interpretive oddity. Perhaps time really is more symmetric than our macroscopic experience suggests. Perhaps influences genuinely flow both forward and backward, with the second law of thermodynamics creating the illusion of absolute temporal direction. The accumulation of evidence is compelling, not definitive. Interpretations without retrocausality remain viable, but suggestive. Multiple independent experiments, different theoretical frameworks, all pointing toward the same unsettling conclusion. Time's arrow may be less absolute than we think. This doesn't mean time travel in the science fiction sense. No one's building machines to visit the past or future. The retrocausal influences are subtle, quantum-level correlations that respect logical consistency. They don't permit paradoxes or causality violations at macroscopic scales, but they do suggest that our understanding of time remains incomplete. Classical physics treated time as absolute, flowing forward uniformly. Relativity made it relative, flexible, interwoven with space. Quantum mechanics adds another layer of strangeness: retrocausal correlations, participatory completion, boundary conditions from both ends of time. The quantum eraser stands as perhaps the clearest experimental demonstration of these temporal anomalies, but it's part of a broader pattern: multiple cracks appearing in time's wall, hints that reality's temporal structure is stranger than our most sophisticated theories currently capture. The disturbing truth accumulates. Time doesn't work the way we think it does, despite all this strangeness. Despite retrocausality and backward influence and future determining past. One thing remains reassuringly constant. The universe doesn't permit logical paradoxes. No matter how disturbing the quantum eraser gets, it never allows contradictions or causality violations that would break logic itself. Consider why you can't send messages backward through time using quantum erasure. The total pattern of signal photons, before sorting, contains no information about future erasure. It's just a random-looking distribution. Only when you correlate signal detections with idler detections, which requires waiting for the idler to arrive, do patterns emerge. This temporal constraint isn't accidental. It's built into quantum mechanics through complementarity and uncertainty principles. You can't gain which-way information and interference patterns simultaneously. You can't measure position and momentum precisely at the same time. You can't extract more information from quantum systems than nature permits. These limits prevent paradoxes. If you could send information backward, you could create grandfather paradoxes, receiving a message telling you not to send it, creating logical contradictions. But quantum mechanics forbids this. The retrocausal correlations exist, but they're only visible retrospectively, after both correlated events have occurred. Think of it as self-consistency enforcement at the quantum level. The universe permits strange correlations, past and future linked in ways that challenge causality, but only correlations that preserve logical consistency. Future measurements can influence past outcomes, but only in ways that don't create contradictions when you know both the past and future. Some physicists call this the Novikov self-consistency principle, proposed for theoretical time travel scenarios. Any system permitting backward influence must self-regulate to prevent paradoxes. The quantum eraser demonstrates this beautifully. Retrocausality exists, but paradox-preventing constraints exist too. Heisenberg's uncertainty principle plays a crucial role. It limits how much information you can extract from quantum systems. This limit prevents you from gaining enough control over quantum processes to send meaningful information backward. You can see retrocausal correlations after the fact, but you can't exploit them for communication. Complementarity also protects consistency. Wave and particle properties are complementary. Measuring one prevents simultaneously measuring the other. Which-way information and interference are complementary. This complementarity ensures that gaining information required to see retrocausality requires waiting for future events to complete. The universe, in essence, protects itself from paradox while permitting strangeness. It's disturbing but consistent, strange but logical, retrocausal but self-regulating. This suggests something profound. Perhaps logical consistency is more fundamental than temporal causality. The universe enforces logic absolutely, but permits causality to be flexible, subtle, bidirectional within logical constraints. Time's arrow emerges from statistics and entropy, not from fundamental logical necessity. Nature has found a way to be both strange and self-consistent, both retrocausal and paradox-free. The quantum eraser reveals this balance, disturbing freedom within inviolable logical constraints. Future can influence past, but only in ways that preserve the coherence of space-time and prevent contradictory outcomes. It's almost comforting in a strange way. Yes, reality is weirder than we thought, but it's weird in mathematically precise, logically consistent ways. The strangeness has rules, limits, boundaries, that keep it from spiraling into incoherence. The quantum eraser might sound like pure abstraction, philosophical speculation removed from practical concerns, but the principles it reveals underlie technologies that already affect our lives and will shape our future in profound ways. Quantum computing represents perhaps the most dramatic application. These devices leverage superposition and entanglement, the same principles operating in the quantum eraser, to perform calculations impossible for classical computers. A quantum bit or qubit exists in superposition of 0 and 1 simultaneously, allowing quantum computers to explore many solutions in parallel. The technology is advancing rapidly, Companies like Google, IBM, and numerous startups have built quantum processors with dozens or even hundreds of qubits. They're already tackling problems in cryptography, drug discovery, materials science, optimization. As systems scale to thousands of qubits, they'll revolutionize fields from artificial intelligence to climate modeling. Quantum cryptography uses entanglement to create theoretically unbreakable codes. Send one photon of an entangled pair to the recipient. Keep the other. Any attempt to intercept and measure the transmitted photon disturbs the entanglement, revealing the eavesdropping. The same quantum principles making the eraser disturbing make quantum communication secure. These aren't distant future technologies. Quantum key distribution networks already exist in China, Europe, and the United States. Satellites distribute entangled photons across thousands of kilometers. The Internet of the future might be quantum encrypted, absolutely secure against any computational attack. The quantum eraser specifically reveals something crucial for these technologies: the importance of information and its accessibility. Whether information about a quantum state exists or has been erased determines physical outcomes. Understanding this relationship enables engineering quantum systems more precisely, controlling decoherence more effectively, designing better quantum algorithms. Even the disturbing aspects have practical implications. The retrocausal correlations mean quantum systems can exhibit correlations stronger than any classical system permits. This enables quantum entanglement to be used for sensing with precision beyond classical limits, for metrology measuring fundamental constants with unprecedented accuracy, for experiments probing nature's deepest structures. The abstract physics of the quantum eraser materializes in devices you might use: quantum sensors detecting gravitational waves, quantum-enhanced medical imaging, quantum random number generators ensuring cryptographic security. The disturbing truth about retrocausality becomes the practical foundation for transformative technologies. It's a reminder that fundamental physics isn't just about understanding, it's about capability. The stranger and more counterintuitive the physics, often the more powerful the resulting technology. We harness quantum strangeness not despite its disturbing features, but because of them. The quantum eraser shows us how reality works at its deepest levels. Understanding that reality, accepting its strangeness, learning to work with rather than against quantum principles, this enables technological capabilities our classical intuitions would reject as impossible. The future is quantum, built on foundations as disturbing and wonderful as the experiment that proves time isn't what we thought. If the past isn't fully determined until future measurements complete it, what does this mean for free will, choice, and moral responsibility? The quantum eraser raises ancient philosophical questions in new quantum dress. In classical determinism, the present completely determines the future. Given perfect knowledge of now, you could predict everything that will happen. Free will seems illusory. Our choices were determined by prior causes, stretching back to the Big Bang. Responsibility becomes questionable if we couldn't have done otherwise. Quantum mechanics complicates this picture. Outcomes are probabilistic, not determined. Even with perfect knowledge of the quantum state, you can't predict exactly what will happen, only calculate probabilities. This introduces fundamental unpredictability, but that's not the same as free will. Random quantum fluctuations in neurons don't make choices free, they make them random. But now add the quantum eraser's retrocausality. If the past isn't fixed until future measurements complete it, perhaps choice gains new meaning. Maybe free will operates by selecting which quantum branch becomes real, which superposition collapses into actuality. Our choice is now reaching back to determine which past we emerged from. It's a strange loop. The past creating us choosing among futures, those choices completing the past that created us. Causality becomes circular, with agency distributed across time rather than flowing strictly forward. We're both products of history and participants in creating that history. Some find this liberating. If the past isn't fully fixed, perhaps we have more freedom than determinism suggests. Our choices matter not just for the future but retroactively for the past, participating in creating the reality we inhabit. Others find it no help at all for free will. Whether the past is determined classically or completed quantum mechanically, Either way, our choices might still be determined by quantum states and dynamical laws. Retrocausality doesn't necessarily mean freedom. It might just mean the determination flows both temporally forward and backward. And pragmatically, decoherence probably destroys quantum effects long before they reach the scale of human decisions. Neurons are warm, wet, complex systems where quantum superpositions collapse almost instantly into classical definiteness. Your brain almost certainly operates classically for all practical purposes, making quantum approaches to free will irrelevant. Yet the measurement problem remains unsolved. We still don't fully understand what measurement means, when superposition collapses, how the quantum becomes classical. Until we resolve this, questions about consciousness, choice, and quantum mechanics remain open. The quantum eraser doesn't solve the free will problem, but it adds a new dimension to consider. If the past can be completed retroactively, if future measurements can determine past states, then causality is stranger and more subtle than classical pictures suggest. Whether this creates space for genuine freedom or just different forms of determination remains uncertain. Perhaps the right response is humility. We don't fully understand time, causality, quantum measurement, or consciousness. We definitely don't understand how they all fit together. The quantum eraser shows us one piece of the puzzle, disturbing but clear. The rest remains mysterious. One of quantum mechanics' deepest mysteries: where's the boundary between quantum and classical? At what scale does superposition vanish, particles become definite, the observer effect disappear? The quantum eraser illuminates this question while reminding us how much remains unknown. Decoherence provides the practical answer. When quantum systems interact with complex environments, air molecules, thermal radiation, measurement apparatus, information about their quantum state leaks into the environment incredibly fast. This environmental entanglement destroys superposition, creating the appearance of classical definiteness. For macroscopic objects, decoherence happens extraordinarily quickly. A dust grain in air decoheres in less than a nanosecond. A person decoheres essentially instantaneously. This is why we don't see everyday objects in quantum superposition. The environment constantly measures them, collapsing superposition faster than we can observe it. But decoherence isn't exactly the same as wave function collapse. It explains why we don't see macroscopic superposition, but it doesn't fully solve the measurement problem. The quantum state, including the environment, still evolves unitarily, still technically exists in superposition. Decoherence makes superposition effectively invisible, but whether it truly collapses remains debated. The quantum eraser operates in a regime where decoherence is carefully minimized. Photons in vacuum don't interact much with their environment. Detectors are designed to register photons cleanly without spurious environmental interactions. The entire apparatus maintains quantum coherence long enough for the eraser effect to become visible, but scale this up, and quantum effects vanish. Try to do quantum erasure with baseballs instead of photons, and decoherence would destroy any interference before you could measure it. The classical quantum boundary isn't perfectly sharp, but it's effectively absolute for macroscopic objects in normal environments. This raises disturbing questions about where we exist on the quantum classical spectrum. Humans are made of particles obeying quantum mechanics. Every atom in your body follows quantum laws, yet you don't experience superposition, don't feel yourself in multiple states simultaneously, don't notice retrocausality in your daily life. The standard answer: you're too big, too warm, too coupled to your environment. Decoherence collapses any quantum superposition you might have before it could matter. You're fundamentally quantum but effectively classical. Yet this leaves questions. Is there truly a sharp transition? Experiments with larger and larger objects in superposition keep pushing the boundary. Physicists have achieved quantum interference with molecules containing hundreds of atoms. The boundary between quantum and classical keeps moving. Some propose that consciousness creates the boundary, that quantum effects continue until they reach awareness. Others suggest gravity creates the boundary, that space-time curvature somehow collapses superposition for sufficiently massive objects. Still others think decoherence is the complete answer, and there's no fundamental boundary, just practical inaccessibility. The quantum eraser doesn't resolve this. It operates firmly in the quantum regime, demonstrating effects that never appear classically. But it reminds us that the quantum classical transition remains mysterious, that we don't fully understand where or how or why the strange quantum world gives way to the familiar classical one. Perhaps you exist precisely at this boundary, quantum at your core, classical in your experience, somehow bridging both realms without fully belonging to either. There's a peculiar peace in accepting that some aspects of reality may permanently transcend human comprehension, not because we're not smart enough, not because we haven't discovered the right theory yet, but because some features of the universe might genuinely be incomprehensible to any finite observer operating within that universe. The quantum eraser shows us something profoundly strange about time and causality. We can describe it mathematically, predict it experimentally, verify it repeatedly, but can we truly understand it? Can we build intuitions that make retro-causality feel natural, obvious, the way classical mechanics feels natural after enough study? Maybe not. Maybe quantum mechanics' strangeness isn't a temporary gap in understanding, but a permanent feature of how the deepest levels of reality relate to our comprehension. We're macroscopic beings who evolved to understand medium-sized objects at moderate speeds. Evolution never needed to give us intuitions about quantum superposition or retrocausality. These concepts might be fundamentally alien to our cognitive architecture. Science has revealed many questions in the past century. What is dark matter? How did the universe begin? What happens inside black holes? How does consciousness emerge from neurons? With the quantum eraser, we can add, how does the future influence the past? Why does observation matter? What is measurement really doing? Some of these questions might eventually be answered. Others might remain permanently mysterious, not from lack of effort, but from fundamental limitations of what observers embedded in the universe can know about that universe. And there's comfort in this, strange as it sounds. It means the universe is larger than our understanding, deeper than our theories, more mysterious than our explanations. It means there will always be wonder, always something beyond current knowledge, always humility available to those who engage with reality honestly. The alternative, a universe completely comprehensible, fully explained, with no mysteries remaining, sounds intellectually satisfying but emotionally sterile. Would you really want to live in a cosmos with no unanswered questions, no remaining puzzles, nothing left to wonder about? The quantum eraser's disturbing truth becomes less disturbing when we accept that disturbance is natural. Of course, reality is stranger than our intuitions. Of course, the universe contains features that challenge our understanding. Why should the cosmos conform to what makes sense to evolved primates on one small planet? Accepting mystery doesn't mean abandoning inquiry. Science continues, experiments accumulate, theories improve, but inquiry can proceed with humility, acknowledging that complete understanding might not be possible, that the universe might always exceed our grasp. This creates space for different kinds of engagement with reality, not just scientific analysis, but also philosophical wonder, artistic expression, contemplative acceptance. The quantum eraser is simultaneously a scientific result to analyze and a koan to contemplate, both precise experimental data and inexhaustible mystery. Perhaps the deepest wisdom is knowing what can be understood and what must be accepted without full comprehension. The quantum eraser falls in both categories, understandable as mathematics and measurement, incomprehensible as intuitive truth. As we near the end of this exploration, perhaps the quantum eraser's most profound implication isn't about time or causality, but about connection. It reveals a universe more unified than our everyday experience suggests, where separation between particles, between moments, between observer and observed, is less absolute than it appears. Entanglement shows us that spatial separation isn't as fundamental as we thought. Two particles, light years apart, remain parts of a single quantum system. Measuring one instantly correlates with the other. The distance between them is real for classical signals and macroscopic objects, but at the quantum level, they're not truly separate. They're aspects of a unified whole. The quantum eraser extends this to time. Signal and idler photons are separated temporally, one detected before the other. Yet their behaviors are correlated across this temporal separation. The signal's wave or particle nature depends on the idler's future fate. Past and future, like space, prove less divided than our experience suggests. This hints at something deeper. Perhaps the fundamental reality is unified, undivided, whole. What we experience as separate particles in separate locations at separate times might be human-scale perspectives on a fundamentally unified quantum state. The separations we perceive between here and there, between now and then, between self and other, might be emergent features of our macroscopic classical experience, not properties of fundamental reality. Some Eastern philosophical traditions have long taught this, the interconnectedness of all things, the illusory nature of separation, the underlying unity of existence. Western science, proceeding independently through different methods, arrives at surprisingly similar conclusions. Quantum mechanics suggests the universe is more like a unified whole that appears multiple from inside, than like multiple separate parts that sometimes interact. You and everything around you emerge from the same quantum substrate. The atoms in your body were forged in ancient stars. The photons hitting your eyes right now traveled from the sun, carrying energy that originated in fusion reactions linking hydrogen nuclei. Every breath connects you to the atmosphere, to plants, to the ocean, to the entire biosphere. And beneath these macroscopic connections lie quantum correlations linking everything to everything else in ways we're still discovering. The quantum eraser makes this visible in a laboratory setting. Two photons, entangled at creation, remain connected across time and space. Their story doesn't divide cleanly into separate narratives. They're one system, one quantum state, one unified phenomenon that we describe in separate terms for convenience, but which doesn't truly separate. This doesn't dissolve all boundaries. You're still distinct from your environment in important ways. Decoherence creates effective separation at macroscopic scales, but it suggests the separateness isn't absolute, fundamental, or irreducible. Beneath the classical world of separate objects lies a quantum world of unified systems. Perhaps this is the ultimate comfort the quantum eraser offers. You're not alone, not separate, not isolated. You're part of a vast interconnected whole, linked to everything through chains of quantum correlation stretching across space and time. The disturbing strangeness dissolves into wonder at the universe's deep unity. Let's take a moment to recognize where we've been together. We started with a gentle invitation into strangeness, a promise that we'd explore something disturbing yet fascinating about reality's nature. Now, having journeyed through quantum mechanics' strange landscape, we can look back and see the path we've traveled. We built foundations carefully: wave-particle duality, the observer effect, entanglement, delayed choice. Each concept strange on its own, but comprehensible, grounded in experimental results that anyone can verify. The double-slit experiment showing light's dual nature, the observer effect demonstrating measurement's role, Einstein's discomfort revealing how quantum mechanics challenged classical intuitions, entanglement proving the universe non-local. Then we assembled these pieces into the quantum eraser itself, Kim's apparatus splitting photons, detecting them separately, correlating signal and idler, the disturbing timing, signal detected first, idler arriving later, yet the signal's behavior depending on the idler's future fate. 4 detection patterns emerging from sorting, 2 showing interference, 2 showing particle behavior, the future seemingly reaching back to influence the past. We wrestled with interpretations, retrocausality taken seriously, future measurements completing past states, many worlds avoiding backward influence through infinite parallel realities, Bohmian mechanics trading time problems for space problems, information-based frameworks dissolving physical properties into knowledge relationships, each interpretation explaining the same experimental results while preserving different intuitive commitments. We explored implications, time's nature questioned, perhaps emergent rather than fundamental, consciousness examined and mostly rejected as explanation, cosmic retrocausality speculated, our observations potentially completing the universe's past, other experiments revealing similar retrocausal patterns. the universe protecting itself from paradox through quantum constraints. We connected to technology, quantum computers, quantum cryptography, quantum sensing, all leveraging the same principles. We considered free will in unfixed time. We located the quantum classical boundary and found it mysterious. We accepted permanent mystery as invitation to humility. We recognized unity beneath apparent separation. Throughout this journey, the disturbing truth remained. The future can influence the past, not metaphorically, not as hidden variables, not as limitation of knowledge, but as genuine quantum correlation transcending time's arrow, verified experimentally, predicted theoretically, undeniable empirically. Yet we're still here. The universe didn't collapse from paradox. Logic remained intact. Reality continues operating according to rules, strange rules, disturbing rules, but consistent rules nonetheless. The strangeness has been integrated, examined, contextualized. The disturbing has become, if not comfortable, at least comprehensible, as the way reality actually works. Multiple interpretations coexist, each preserving different aspects of our intuitions while sacrificing others. Science honestly grapples with reality's complexity, proposing frameworks, testing predictions, accepting mysteries where they appear. The quantum eraser stands as testament to both human ingenuity, building apparatus subtle enough to catch reality in the act of violating causality, and reality's inexhaustible strangeness. As we prepare to conclude, perhaps the deepest lesson isn't about physics, but about how we relate to knowledge itself. The quantum eraser disturbs us precisely because it challenges what we thought we understood about time, causality, and reality. But disturbance can be productive, healthy, even peaceful when we approach it with the right attitude. The universe is under no obligation to make sense to us. Our intuitions evolve to navigate a specific environment, medium-sized objects at moderate speeds in classical regimes, reality at quantum scales, at relativistic velocities, at cosmic distances operates differently. Our incomprehension isn't nature's failure, it's a reminder of our limitations. Classical experience taught us to expect certain features. Objects have definite positions, causes precede effects, the past stays fixed. These heuristics work brilliantly for everyday life, but they're local adaptations, not universal truths. At deeper levels, reality refuses to conform. Finding peace with this requires relinquishing the demand that the universe match our expectations. It means accepting that our most certain intuitions might be wrong, that reality's strangeness might be permanent, that some aspects of nature might transcend our comprehension. This isn't defeat, it's intellectual humility. It's recognizing that we're small beings in a vast cosmos, using finite minds to understand infinite complexity. That we understand anything at all is remarkable. That some things remain mysterious is natural, expected, perhaps inevitable. The quantum eraser becomes less disturbing when we stop demanding it make intuitive sense and simply accept it as how reality operates. Future influences past. Measurement determines outcomes retroactively. Time's arrow is less absolute than it seems. These aren't problems to solve, they're truths to accept. And acceptance brings peace. Not the peace of complete understanding, but the peace of acknowledging our limits. Not the certainty of explanation, but the comfort of honest engagement with mystery. Not the triumph of solving puzzles, but the humility of recognizing some puzzles exceed our solving. This shift in perspective transforms the disturbing into the wonderful. Yes, retrocausality challenges our intuitions, but it also reveals how much richer reality is than our imagination suggested. Yes, quantum mechanics refuses classical explanation, but it also demonstrates nature's inexhaustible capacity to surprise us. The peace beyond understanding isn't ignorance, it's acceptance. It's engaging with reality as it is rather than demanding it be what we want. It's finding wonder in strangeness rather than anxiety. It's letting go of the need to force everything into familiar categories. The quantum eraser remains disturbing in the sense of being counterintuitive, but disturbing can coexist with peaceful when we stop fighting the strangeness and let it expand our sense of what's possible. The universe is stranger than we imagined. That's not a problem. That's an invitation. Despite everything we've explored, retrocausality, quantum superposition, the measurement problem, temporal strangeness, your everyday experience remains valid and real. You exist as both quantum entity and classical being, with both perspectives true simultaneously. At your most fundamental level, you're quantum mechanical. Every atom in your body obeys quantum laws. The electrons in your brain exist in quantum states. The chemical bonds holding molecules together are quantum phenomena. The electromagnetic forces letting you see, touch, and interact with the world are fundamentally quantum. You are at base a quantum system, yet you experience yourself classically. You feel located in one definite place, not spread across multiple positions. You remember one past, not superposition of many pasts. You make choices that feel singular, not quantum branches splitting reality. You live in a world that seems classical, solid, definite, following intuitive cause and effect. This isn't contradiction, it's scale. Decoherence ensures that quantum effects vanish at human scales. Your quantum nature remains fundamental, but it manifests classically because you're large, warm, and constantly interacting with your environment. The quantum substrate supports classical experience without negating it, so when the quantum eraser reveals retrocausality at photon scale, this doesn't mean your past is unfixed or your memory is unreliable. At your scale, the past is effectively determined, recorded in countless entangled environmental degrees of freedom. Decoherence happened essentially instantaneously, collapsing quantum superposition into classical definiteness billions of times per second throughout your life. The quantum world and classical world coexist as different valid perspectives on the same reality. Quantum mechanics is more fundamental, it's the deepest description we have, but classical mechanics emerges from quantum mechanics in the appropriate limit, describing macroscopic objects accurately. Both are true, applying at different scales. You don't need to choose between quantum uncertainty and classical definiteness. You embody both. You are simultaneously a quantum system governed by superposition and entanglement, and a classical being experiencing definite states and forward causation. The same laws permit both mystery and stability, both strangeness and familiarity. This is perhaps the most important takeaway. Quantum mechanics' disturbing features don't invalidate your experience. Your life, your choices, your memories, your relationships all remain real and meaningful, even if the underlying physics is strange. The strangeness operates at scales beneath everyday awareness, supporting rather than undermining the classical world you inhabit. So rest easy. The quantum eraser reveals deep truths about time and reality, but it doesn't make your world less real. It makes the foundations richer, stranger, more wonderful than classical physics suggested. You stand on quantum foundations, experiencing classical stability, bridging both realms, fully belonging to this strange and beautiful universe. Our journey is complete now. We've traveled from simple questions about light passing through slits to disturbing truths about time itself. We've witnessed the future reaching back to influence the past. We've grappled with interpretations. We've explored implications. We've accepted mystery. The quantum eraser experiment proved something extraordinary. Reality is stranger than our most sophisticated theories predicted. Time's arrow bends in ways we're still understanding. Causality is more subtle than classical physics suggested. The universe contains correlations and connections that transcend our intuitions about how past and future relate. But the disturbing has transformed through our exploration. What began as unsettling, future-changing past has become remarkable, wonderful, an invitation to expanded understanding. The strangeness remains, but it's no longer threatening. It's simply how reality works at its deepest levels. Perhaps as you drift towards sleep, your mind can relax into this new understanding. The universe isn't broken by retrocausality. It's richer, more interconnected, operating according to rules that transcend classical common sense but remain mathematically precise and experimentally verified. Time continues its mysterious dance, flowing forward in our experience, while permitting backward correlations at quantum scales. The future has always been influencing the past in subtle ways we're only now learning to detect. This is natural, normal, the way things have always been. We've simply uncovered it, brought it into awareness, examined it gently, and now, with understanding comes release. You don't need to solve the measurement problem tonight. You don't need to choose between interpretations. You don't need to fully comprehend retrocausality. These mysteries have waited billions of years. They can wait while you rest. Let your thoughts drift like photons in superposition, exploring multiple paths simultaneously. Let your awareness spread like waves interfering, creating patterns of rest and wakefulness. Let the quantum strangeness of reality cradle you gently, reminding you that the universe is larger and stranger and more wonderful than our waking minds can hold. The quantum eraser's truth remains. The future has always been changing the past. We're always completing history through present observations. Time is less fixed than it seems, reality more participatory than we imagined. But this truth doesn't demand anything from you now. It simply is, like gravity, like quantum mechanics, like all the laws governing the cosmos. You can rest in it, knowing that tomorrow the universe will still be strange and beautiful, still operating according to rules we partially understand and partially wonder at. The photons are still entangled, the patterns still emerge, the mystery endures. Good night.